Law, it's open.
You can come in.
Okay, so let's talk about ellipses for those of you that are math nerds. How many foci does an ellipse have? Two. What do you call an ellipse that only has one foci? A circle. Okay. So, what he figured out, and he actually got lucky. So, the amount of distance between the two foci, and the sun is at one of them. The other one's just a point out in space. Is the eccentricity is a measure of basically how far apart the two foci are. So it's been estimated that if the eccentricity of Mars is about 10%. So Tycho Brahe had good enough data that he could pick up that eccentricity. Okay? What they think might have happened if the eccentricity had been much less than that, probably about 5 to 6%, if it had only been that amount of eccentricity, the first law would probably have been the law of circles, okay? And he would have probably thought, oh, the planets just move in circles. But that's what everybody wanted, okay? And here's the reason why. So, if you go back to the Greek philosophers, Aristotle says, oh, the natural state of motion on objects on Earth is to be at rest. He was all about natural states of motion. The reindeer is always going to come to a stop when I slide the reindeer. If I drop the ball and bounce it, what's it always going to do? Come to a stop. Okay? So on Earth, the natural state of motion was to be at rest. The heavens, where the sun, the moon, and the stars move, they viewed that as like the realm of the gods. And they thought the circle was the perfect geometric shape. It has no beginning, it has no end, all points are equal distance from the center. Cool. And so everybody thought, because you're tracking the planets and the planets move in the heavens, and the circle was the perfect geometric shape, that everybody thought the planet should then naturally move in a circle. Okay? So when Kepler came out with his first law, and it was actually the law of ellipses, and some planets are very high vertical orbits. The Earth has an eccentricity of about 3 to 4%. So,
Can I get Shannon's
So, this was controversial because it was like God was trying for a circle. He had a bit of an off day, and we had to settle for like an 8. Okay? So people actually first did not appreciate the idea that they traveled in ellipses. So there isn't anything necessarily magic. It isn't like, oh, the universe has to have ellipses. But what does happen, and when we get into angular momentum, you'll see that it is an ellipse, and it still follows all the laws. It follows the laws of conservation of energy. It follows the law of angular momentum. But because it's an ellipse, something weird happens. Okay, so this leads to the second law. So the second law is this. It's a law of equal areas in equal times. So we got to do a little bit of geometry on this one, not much. So here's the star, here's this orbit. So, and you had to kind of view this in sequence. So this is after Kepler had figured out a way to determine the radius of the orbit, okay? So he went in and he drew a line. So he drew a line from the sun out to the edge of this orbit. And again, it isn't like you can see the orbit. Like, if I throw something to the back of the room, I know it can't go farther than the wall, because I can see the wall. And I know that's as far as it's going to go. When you look at the planets, there is no wall. All you see is dot in the night sky against a vast background of nothing behind it. But at this point, he knew the orbit. So he said, okay, maybe on May 1st, October 1st, pick a date, it's at this point. Then maybe 30 days later, on May 30th, it would have moved to this point. So he could go in and he could calculate that area. And the formula that he used was area equals theta over 360 times pi r squared. So the theta is how many arcs of tangent it moved through. Did it move through 10 degrees? Did it move through 15 degrees? So this angle is the theta. That tells you how much of the circle that you're looking at, okay? Out of 360. Got pi, you have the radius. Now let's talk about the radius. Kepler struggled mightily with distances because it isn't like he could ask his phone and go, hey, what's the distance from Mercury to the sun or Mars to the sun? Yeah, nothing. He started over from scratch. So if you're Kepler and you're doing these calculations by hand, what's the favorite number that you want to use? 1. Okay? You want to have a numeric value of 1 every chance that you can. So what Kepler did is he said, okay, I don't know the distance from the Earth to the sun, but I'm just going to make that 1 astronomical unit. Okay? Unit. Usually it's just, we're just always going to call it AUs. Okay? So the distance from the sun to the Earth is 1 astronomical unit. So obviously the orbital radius of Mercury and Venus is going to be less than 1. Mars, Saturn, Jupiter, everything else is going to have an orbital radius greater than 1. Okay? So this radius then in weird units are AU squared. Okay? So what he would do is say, okay, here's the sun, here's Mercury, whatever, pick a planet. On May 1st it's here, on May 30th it's here. He would know how many degrees it swept through, and then he would know the 2 radii, and he could calculate that area. Cool. Then when it was closer, he'd do the same thing. Again, this is why it's equal areas and equal times. So then he'd go, okay, maybe this is October 1st to October 30th. Still a 30-day period, okay? But this obviously here has a much smaller radius. But what he found is that these 2 areas are the same. So the only way the areas can balance out is if you have a smaller radius, what has to happen to that value of theta? It has to get bigger. And that's the part of the arc that it sweeps out. So what he concluded from this, and this is where it gets a little bit weird, because everybody thought it shouldn't happen. So when you increase the radius of the orbit, it goes slower. So there's an inverse relationship between radius and velocity. So when the planet's at its furthest point, it's going to be going slowest. When it's at its closest point, guess what?
Fastest.
That's when it's going to be going fastest. Later on, you'll see that has to happen from the law of conservation of angular momentum. That'll be the next unit. But just remember this. It also has to happen that way to conserve energy. So there's 2 reasons why, if you're in an elliptical orbit, it has to do that. So this created a problem. It's like the planet's speed isn't constant. But again, I don't want you to think like, oh, you see like streaking across the night sky. It's still rising in the east, it's still setting in the west. But what you're talking about is the speed that it moves relative to the fixed points in the sky of the constellation. So when it's closest, you're talking about how it moves relative to the 3 stars over Orion's belt, okay? It isn't talking about how fast it's moving across the night sky. You're talking about the movement relative to the fixed points, okay? So, we got that one. Smaller, here's all I need you to remember out of this. As the radius gets smaller, the velocity gets bigger. So if you've ever done this, like if your house has like a banister on the end of the stairs, and this is really cool, especially if you have like a wooden floor, and you go running past it, and you grab a hold of the banister, and you like slingshot yourself around. You ever do that? Okay, all right, know what I'm talking about. You have a visual. That's basically what the planets are doing when they slingshot around the sun. Okay, they reach out, grab the sun, boom, okay, go relatively fast as they go around. But then when they go away, they slow down. It's like, oh, we're storing energy, okay, because we're going further away. And they speed up like, boom, fast, and then they slow down and they go. That isn't the noise that they make, by the way. It's like, do they really make that noise? No, they don't. But you get the idea. Okay, so stand up. Take a stretch if you want to, because the third law is going to take a while. So stop that.